All right, so the do now. The first question, we're looking at an isotope of iodine, and I need you to tell me how many protons, neutrons, and electrons there are in this isotope. So what did you get for the protons? And where'd you find that information? Yeah, it's the periodic table. You look up iodine, and the atomic number is the one that's above it. It's a whole number. And the atomic number is equal to the number of protons. And that's 53 for iodine. What about neutrons? How many neutrons are there in this isotope? So let me write a few notes down here just in case people need to reference it. So to get that 74 neutrons, you had to recognize that the 127 is the mass number. So that 127 is equal to the number of protons plus the number of neutrons. And since we already know the number of protons from the atomic number, we can solve for the number of neutrons, and that should be 74. The last part of this question is the number of electrons. So how many electrons are there in this isotope? Exactly. There should be 53. It's a neutral atom. It's not an ion. That means that the number of protons is equal to the number of electrons. Are there any questions about this first one? Y'all did pretty good, so I'm going to move on. What about the second one? Iodine is best described as a metal, non-metal, or metalloid. A, B, or C? It is a non-metal, so B. And that's just from knowing the periodic table and that iodine is on the far right of the periodic table. And that's where the non-metals like to hang out in their own little corner. For this next question, I'm going to move on to a new slide so I can work it out for you. But just out of curiosity, what did we get? I'll put the answers that we got along the top, and then I'll work it out and see if we agree. Does anyone else want to share an answer? Ayana, is that decimal point in the right place? So we've got a few answers. They're all kind of in the same ballpark. Okay. So let's go through and solve it. We have this element X that occurs naturally as X6, and its atomic mass is there, and X7. Calculate the atomic mass given that the natural abundance of X7 is 92.5%. I always start with making my chart. We've got these two isotopes, X6 and X7. We know the percent abundance for X7 is 92.5%. How would we write 92.5% as a fraction? We just put the number over 100. So that's the percent abundance of X7 as a fraction. Let's fill in our last column here with atomic mass. Now notice we do not have the percent abundance for X6. How do we figure that out? You have to subtract 100% minus the percent abundance of X7. Since there's only two of them, that's all you have to do. So when you do that, you know what? I should have wrote that much smaller. Let's try that again. So when you do that, you should get 7.5% abundance for X6. That was the key point. If you could not figure that part out, you couldn't solve the rest of the problem. Now you can fill in the percent abundance written as a fraction, and you can do your multiplication and addition. So in order to do the sig figs correctly, you need to calculate each part individually. So the contribution from X6, with sig figs taken into consideration, is 0.45 AMU. The contribution from X7 is 6.49 AMU. And when you add those two together, you get 6.94 AMU. So if this were a chapter check-in and you gave me the right number of sig figs, I would have accepted those two answers as well because they're pretty close. Yes. So here's how we did the sig figs. For the x6, we can only have 2 sig figs here because of the 7.5. For the x7 number, we have 3 sig figs. But when we're adding, remember, we don't care about the number of sig figs. We care about the number of places. So they both have to the 100th place. So that's how we can keep all 3 sig figs. Is that clear? You're welcome. Other questions? So overall, how did this, the do now feel? Did it feel like, okay, I think I got the first part of chapter 4. I think I'm solid. Or do you feel like, might need to do some more practice? Yeah. So if you're like, I think I'm good, or need to do a little bit more practice, but I'll be straight, that's a good place to be. Speaking of which, if you need more practice, I put out an announcement a couple of nights ago, but I tallied up all the votes for when people want office hours, and Wednesday afternoons from 2 to 4 p.m. won. If that time does not work for you, you can always try to set up an individual meeting by sending me a message through course messages. I'll bring this up again at the end of class when I do reminders. But I just wanted to plug it now, because if you feel like you need more practice, if any one of these 3 problems was difficult for you, you should definitely visit office hours, or at least reach out to me and let me know. So let's move on. Now we're going to finish up chapter 4. There's only a couple of sections left, but 2 of them are a little bit abstract, so it might take a little more time, and that's why I broke it up like this. The first section we're going to talk about is electron energy levels. We need to talk about the electromagnetic spectrum, and hopefully you were able to watch the video before this class, because I am not going over every single detail. So if you have not been able to watch the YouTube video for chapter 4 part 2, you definitely still need to do that, because there's some details that you're going to miss out on if you don't. So the electromagnetic spectrum. How many people have seen this before? By a show of hands, or you can say me. So if you had physics or if you had chemistry in high school, this is probably something that you've seen before. All this is looking at all the different wavelengths of light. And we're going to talk about some of the characteristics here. The way that this particular spectrum is set up is on the far left, we've got the longest wavelengths. So that's a representation of a long wavelength, all the way to the shortest wavelengths. I'm a scientist, not an artist, so don't judge. The characteristics that we associate with a longer wavelength is low energy and a low frequency. And the converse is true for a short wavelength. They are higher in energy and they have a high frequency. So you will need to know the relative order of these different waves. So we've got radio waves. So if you listen to the radio on your way to or from work, or if you commute to campus or anywhere else, you'll know radio waves. Microwaves, if you heat up your food in the microwave, then you're very intimately familiar with those. Infrared, you may or may not. So heat lamps, night vision goggles, those kinds of things use infrared. Those are on the lower end of the spectrum in terms of wavelength. So they're longer wavelengths, lower energy, lower frequency. Then we hit the visible portion. That's what we see. So you'll need to know the colors of the rainbow: red, orange, yellow, green, blue, indigo, which is like a dark blue, and violet. When I learned it, I learned Roy G. Biv, and that helps you keep the order straight for the rainbow. So that's the visible light section. And we're still going from longest wavelength to shortest wavelength in here. So red light has the longest wavelength out of visible light, and violet light is the shortest. After the visible spectrum, you've got ultraviolet light. So that's like from the sun. That's why you wear sunglasses. That's why you put on sunscreen, hopefully, when you're outside during the really high intense sun intensity times of the day. Then there's X-rays. If you go to the dentist, they check your teeth. If you've broken a bone, hopefully not, but they'll use X-rays there too. And then we've got gamma rays and cosmic rays. Those are really high energy. So you'll need to know, again, the relative order, and know that, relatively speaking, the longer wavelength is going to have lower energy, a lower frequency. The higher, or the shorter wavelength is going to have higher energy and higher frequency. So are we clear on what you need to know from here? Great. So let's do a quick practice. Which wavelength of light has the lowest energy? A, B, C, or D, or E? They're all the same. We've got one answer. So the lowest energy is going to be the longest wavelength, which this is a lambda. That's for wavelength. We've got an answer change. So the longest wavelength is B, right? So don't be tricked by that, because it's the lowest number. We're talking about the length. Nanometers is a length. So 650 nanometers is the longest wavelength, which means it has the lowest energy. 200 nanometers would actually be the highest energy. So I chose this question specifically because it's one of those gotcha questions that if you don't read it and think it through for an extra 5 seconds, you might put the wrong answer and then be like, man, I should have known that. So don't lose those easy points. We clear on this one? All right. So we've talked about light energy. We talked about waves. Now we're going to relate that information to electrons and energy levels. So remember, in the first part of chapter 4, we were talking about the structure of an atom. Now we're talking about where the electrons are within the atom. We know they're outside of the nucleus, but we need to be a little bit more formal in our definition of that. And there were several models of the atom that led to where we are today, which is the quantum mechanical model. And one of the additions that was made by Niels Bohr, I don't think you need to know that name for this class, but he was the one who came up with the idea of energy levels. All electrons that are within the same energy, they're grouped in the same level. So if you think about going to the library, which I don't even think libraries and towns and stuff are open, but remember that day when you could go to the library and the books are organized, alphabetically. So all of the A's, all of the B's, all of the C's. It's the same thing with electrons. All of the electrons that have the energy equivalent to n equals 1, they're going to be in that level. If they've got a bit more energy, they're going to be in the next level. These energy levels are assigned values called principal quantum numbers. If you look at the rows of the periodic table, that's what the n's equal to. So the first row is n equals 1. The second row, which remember the rows are periods, that's n equals 2, and so on, and it goes all the way down to 7. The higher the n value, the more energy your electron is going to have to be in that level. And the farther away from the nucleus those electrons are going to be. So if this is an n equals 1, and this is an n equals 4, and I'll use red to show where my electrons are, you can see that the electrons are much farther away from the nucleus. So as you continue down the rows or the periods of the periodic table, the energy levels are getting bigger and bigger and bigger, and the electrons in that energy level are getting farther and farther away from the nucleus. Are those concepts clear? Because we're stepping into some real abstract territory. So I'm going to be asking a lot of questions and making sure that you're okay. Because if you miss any part of it, then it's going to be difficult for you to put these concepts together and start answering questions. So I apologize if you feel like, man, she just keep asking if we're okay. It's on purpose because it's very easy to get lost. So we talked about electrons, same energy level. Yes, question. So yes, you do have more electrons if you are filling all of the energy levels, but let's not talk about number of electrons. What we're talking about is just if you have an electron in n equals 4, it's farther away from the nucleus than n equals 1. Other questions? If not, you can give me a thumbs up or say you're ready to move on. Okay, I can repeat that. So the first point is that electrons are grouped together if they have the same energy. So every electron that has enough energy for level 1 is going to be on level 1. Level 2, electrons are going to be on level 2. And those levels are called principal quantum numbers, which is abbreviated with an N. Each n is associated with one period on the periodic table. So each row from 1 to 7 is an n, an energy level. And finally, the higher the n value, the higher energy that electron has to be there, and the farther away that electron is from the nucleus. So if you have electrons in n equals 1 versus n equals 4, those electrons in the n equals 4 have more energy and they're further away from the nucleus than the electrons in n equals 1. So that's the summary of this slide. Again, let me know if you're good or if I need to go over a certain point again. And as always, this is going to be uploaded to YouTube, and I'll put the link in. Because I teach multiple classes on Tuesdays, it doesn't happen until the evening. But if you check back late tonight or first thing tomorrow morning, you will see the links. I always post the annotated lecture notes, so what you see me scribbling down, that's always posted on Blackboard pretty quickly. But the video itself takes me a little bit more time. So if you miss something and you're like, I think I need to hear that 5 more times, or you like the smooth melodic sound of my voice, it's okay. The video will be posted on YouTube. So we talked about these electron energy levels. Electrons can move to different levels based on if they absorb energy or release energy. So let's say that we have an electron in n equals 1, and I'm going to use an arrow as an electron. If I want to get that electron to the n equals 2, I have to add energy in. So that electron is going to absorb a photon so that it can move to the next energy level. After that electron has had its fun in n equals 2, it may fall back down to n equals 1. It's going to emit a photon. Now, a photon is just a package of energy, light energy. And you have to have the specific amount of energy required to move up or down an energy level. There's no such thing as moving to n equals 1.5 because it doesn't exist. The energy that is emitted or absorbed has to be equal to the difference between the two energy levels. So talk to me. How does that sound? Can I ask you a practice problem, or do you need me to go over this information again? Okay. So let's do it again. We'll do it a slightly different way. I'm going to change colors. We'll go over that, the difference. So we'll start with, oops, I didn't mean to do that. We'll start with the first example. I have an electron in n equals 1. And I want to get to n equals 2. To do that, I have to add a photon of light. You need energy. So that's what we're saying here. Plus a photon means plus energy. If I'm going to go down in energy, say the reverse, I'm starting in n equals 2, and I'm going back down to n equals 1, I'm going to lose a photon or emit a photon. Because remember, n equals 2 is a higher energy level. So to get there, you need more energy to be further away from the nucleus. But if you're going in the reverse direction, n equals 2 to n equals 1, n equals 1 is a lower energy level. So you're going to have to release some of your energy so that you can hang out a little bit closer to the nucleus. The difference between the two energy levels, we're talking about a certain amount of energy. So you need some number of joules of energy. If you've ever played a video game where you have to gain experience points to level up, it's exactly like that. So if you're at level 1, experience level 1, and you're trying to get to level 2, you have to do certain things in order to earn enough experience points to move up to the next level. If you're a little shy, you're still at experience level 1. So it doesn't matter how many points you have until you've crossed the threshold of having enough experience points to be qualified as level 2. So that difference, let's say that you need to earn 5,000 experience points. That's the difference between level 1 and level 2. With our electrons, we're talking about energy. So maybe it's 5,000 joules or whichever energy unit you want to use. That's the required amount of energy to take an electron from level 1 to level 2. So does it make a little bit more sense the second time around? Again, this is an abstract concept. You can't see electrons. And we're only going over a few sections, but they take time. And the goal for this class is not for you to be able to take a test right after today's lecture, but for you to be able to go back and look at your notes, try some practice problems and say, okay, oh, that's what I'm missing. Or, you know what, this part doesn't make sense to me still. So it may be the first time you're hearing this or the second time, but you should be improving your understanding. You may not have it 100%, but you should be improving. So let's press onward. We talked about energy levels with electrons. We can break those energy levels into sub-levels. So if we have energy level 1, this is kind of our main energy level. We're looking at the first row on the periodic table or the second row on the periodic table. Within that, there are sub-levels. Those sub-levels are S, P, D, and F. S is the lowest energy, and F is the highest. Each of these sublevels do not exist in every single energy level. In n equals 1, you only have the S. In n equals 2, you have the 2s sublevel and the 2p. In n equals 3, you have the 3s, the 3p, and the 3d. So there's a specific order to which energy levels have which sublevels, and which sublevels are filled first within a main energy level. And when we start talking about that, we're going to be ready to talk about electron configurations, where electrons are in an atom. So does everyone understand the concept of these big energy levels being split into sublevels, and those sublevels have varying amounts of energy? Does that concept make sense? And if you're lost, it's okay. Let me know. Okay, one more time. We've got main energy levels. So the n equals 1, n equals 2, n equals 3. Within those big energy levels, we have sublevels. So if you think about a mall, like a real indoor mall with multiple floors, you don't just walk in and it's just mall. There's different stores, there's kiosks, there's a food court. It's sectioned off, right? It's the same way with energy levels. There's these main floors, the energy levels, and within that, there are sublevels that have varying energies. S, P, D, and F are the types of sublevels, S being the lowest energy, and F being the highest. Each energy level has certain sublevels associated with it. Is that more clear the second time around? Okay, great. Yeah is okay. I'm not offended. So let's press forward a little bit more. So we have the idea of these energy levels, the big main floors. We break up those floors into sublevels of varying energy. Now we have to talk about the placement of electrons into these levels and sublevels. One thing you have to remember is that electrons have a charge. I know, it's groundbreaking. They have a charge. They're negatively charged. And things that have the same charge don't exactly want to hang out next to each other. That brings us to the Pauli exclusion principle. Each of these orbitals that we're talking about, so we said the different energy levels and sublevels, we have S, P, D, and F. Each of those has a certain number of orbitals, which we're going to get into that in just a minute. But they can only hold 2 electrons because the electrons in the same orbital are going to repel each other. They have the same charge. Negative and negative, no, they don't want to be next to each other. So they have to have opposite spins. So what that means is that if I have a 1s orbital and I want to have 2 electrons in it, and I'm using the arrow to show which way they are, I can't put 2 electrons with the same spin. They're both spinning in the same direction. They're going to hate each other. Can't do it. Likewise, if I put them both spinning like this, no, they don't like it. They don't want to be that close together. They don't want to be holding hands. You have to have opposite spins, which is represented by an arrow going up and an arrow going down. I always teach this as if you've ever had family coming over If you don't have a big house like we did not when I was growing up, your cousins came into town or something, they drove for however many hours. I'm from Jersey. I have family in Georgia, family in Virginia. They would, one set of family would drive up to Virginia, and then other people hop in. Everybody drives up to New Jersey. A lot of female cousins on my mom's side. So that meant I was sharing my twin size bed. Head to foot, foot to head. That's just what it was. You ain't trying to sleep head to head. You ain't trying to sleep like that, okay? You're going to be punching each other in the face by accident. It's not going to be fun. So you got to have your head next to somebody's feet so that maybe they won't kick you. They might flail their arms, but they may not kick you in the face. So if you had that experience where you've had to share your bed with someone, that's exactly what these electrons are like, okay? So, little anecdotal story for you there. So we're building here. We've got energy levels. Like n equals 1. Then we have sublevels. Like the 1s. And then we've got these orbitals. So I'll give you another example of a sublevel, would be 2p. An orbital might tell you a little bit more about its geometry. So 2px or 2py. Don't worry about that terminology right now. But these are the things that we're trying to build. And what we're talking about with the orbitals is that if I have something, say, in the 2px orbital, that if I have 2 electrons in there, they have to be spinning in opposite directions. So does the Pauli exclusion principle make sense? And then when we talk about energy levels and sublevels and begin to talk about orbitals, do those things register? So it's a 2-part question. Again, don't shy away if the answer is nope, I don't get it. That's okay. If you knew it, you wouldn't be in this class. So you can break down the sublevels into orbitals. And each of those orbitals can hold 2 electrons. We're getting to that point. So I haven't fully described orbitals yet. We're going to press on just a little bit because it may help clear some things up. So we're building all this information to be able to draw orbital diagrams and write electron configurations. And that will give more detail about where the electrons are in an atom. What I want you to do is look at a periodic table and tell me how many electrons should neon have. So the atomic number for neon is 10, which means that it's going to have 10 electrons. The orbital diagram is going to show where those electrons are and how many electrons are in each orbital. So I'm going to write out some energy levels and sublevels, and then we're going to draw this out. We'll do another example like that, and then I'm going to write out the full how you would fill all of these energy levels and sublevels. So just bear with me for a little bit and just take my word when I give you the order for how things are filled. So you may see boxes. I do lines because a line is easier to draw than a box. Okay, so I've drawn out some sublevels and broken down the orbitals a little bit more. So for the S sublevel, there's only one orbital. In the P sublevel, there are 3 orbitals, and each of them can hold 2 electrons. In the D sublevel, there are 5 orbitals, and in the F, there are 7. So you don't need to know the specific geometry. And I do go into the shapes of the different orbitals in the YouTube video for this part of chapter 4. So you will be responsible for that. But that part, knowing the shapes, is easier than understanding the concept of sublevels and orbitals. So again, S sublevel, 1 orbital. P sublevel, 3 orbitals. In this case, the 2px, 2py, and 2pz. You don't need to know this specific information about the x, y, and z, but you do need to know that the P sublevel has 3 orbitals. The D sublevel has 5 orbitals, and the F sublevel has 7 orbitals, and each of them can hold 2 electrons. We need to place 10 electrons for neon. Yes, what's your question? No problem. So the way that we're going to fill this with electrons is we're going to start with the lowest energy level and the lowest sublevel. So that is the 1s. That's the lowest energy that we have. We can fit a maximum of 2 electrons in each orbital. There's one 1s orbital. So we're going to put 2 electrons in there with opposite spins. Now after that, we still have 8 more electrons to place. So we move on to the next energy level, which is the 2s. And we put another 2 electrons there. Now we've got 4 electrons, and we've still got 6 left to place. The 2p sublevel has 3 orbitals. So that means that it can hold a total of 6 electrons. We're first going to go through and populate each orbital with 1 electron. We still have more electrons to place. We have another 3. So then you go back and fill in and double up where you have to. Now for neon, you're going to fill all the spaces. But let's say we didn't have neon. Let's say we had fluorine. Fluorine has 9 electrons. This almost looks a little bit like a game of Hangman. All right. I don't even know if people play Hangman anymore. I might just be that old. So we're going to go and fill in our 1s and our 2s the same way. And that's 4 electrons. But for fluorine, we've only got 5 more to place. 1, 2, 3, 4, 5. And one of them is left unpaired. So you're always going to want to fill your orbital diagrams. If there's more than one orbital, fill with 1 electron first, then go back through and fill in and double up as you need to. So does just the concept or the idea of filling in the electrons, doubling up when you have to, does that part make sense? Just the last part that we did. What's your question? No. So you would need more energy levels. Each orbital, each of these lines represents an orbital. And you can only hold 2 electrons in each. I already knew that we would only need these specific orbitals. But if you were doing an element with more electrons, you would need more orbitals. Okay. Yes, question. So when you look at the periodic table, the atomic number is 10. That tells you that you have 10 protons. In a neutral atom, the number of protons is always equal to the number of electrons. So if you have 10 protons, you have to have 10 electrons as well. No problem. That's a good problem to have because it's easily solvable. So let's do another example and walk through that. And then we'll let it marinate and you can take a short break. Because I know your brain may be about to explode. I don't want that to happen. So look at your periodic table and tell me how many electrons silicon has. And it should have 14 electrons. Now, what period is silicon in? Which means which row is it in? It's in the 3rd period. So that means that we're going to need energy levels and sublevels that go up through energy level 3. So that's kind of going back to that last one of the questions we just had about how do you know how many orbitals and things you need. You know based on the placement of the element. We're in the third period, so we need to have all of the sublevels and orbitals for the third period. So you always start with 1s, 2s, and the 2p. The next thing you fill is the 3s, followed by the 3p. So I'll fill these in. I'll give you the full order of how things are, how electrons are loaded, and then we'll take a break and you can kind of figure out what your questions are. We can address those and move forward. So that's the plan. We said that there are 14 electrons to place. You always start by placing them in the 1s, and you fill the 1s with 2 electrons. Then you fill the 2s with 2 electrons. Then you're going to fill in the 2p. Still don't have enough, so we're going to fill again. So now we've got a total of 2 plus 2 plus 6 electrons. So we filled the 2p all the way up through the 2p, and we have 10 electrons total. We still need to place another 4 electrons. We're going to fill the 3s, and that gives us 12 electrons. Then we're going to place the last 2 electrons in the 3p, and we're not going to pair them up because they don't want to be paired up unless they have to. And that gives us 14 electrons. Now, if you had a much bigger element that you needed to do this for, you would need a lot more orbitals. So I'm going to write for you the full configuration for how you would fill these things, starting with the 1s and going all the way up through the 7th energy level. Make sure you have this in your notebook. And you'll notice these superscripts here. That's going to tell you the way that I'm writing. That's the number of electrons. And I'm writing down the maximum number of electrons that can fit in each sublevel. So we know that the S has only 1 orbital. It can fit 2 electrons. So for the 1s, you're going to put a 2. For the 2s, you're also going to have a 2. The 2p, we said there are 3 orbitals there, and they can each hold 2 electrons. So there's a maximum of 6 electrons that you can hold there. Notice how I went from 3p6 to 4s2. Even though the 3d has a 3 in front of it for the main energy level, it is actually slightly higher in energy than the 4s. So I didn't make a mistake. This is the order. you'll notice again the same thing in the 5th energy level. You're filling the 4D sublevel. And I'm going to do a more visual way of this using a periodic table after we come back. But for now, just trust me and write this down in your notebook as I write it. So that is the full order of all the electron energy levels and sublevels on the periodic table as we know it today. So if you had to draw an orbital diagram, you have the complete order, and you could do it for any element on the periodic table. If you want to throw a question up now, you can. Otherwise, we can take a 5-minute break for you to shake your brain out and see what questions you might have. So how many of you want to go straight to break without talking about this, and then we just come back and start with this? Yeah, I think it's time for a break. It's getting a little abstract. So let's take 5 minutes. It's 12:13. So we'll break until 12:18. I'll see you back then. All right, everybody. It's 12:18. So we're going to get back to it. I know this chapter is getting a little heavy. But what we just did was we wrote an orbital diagram for silicon. It's a 3rd period element, which means that we needed to have sublevels in the 3rd energy level to accommodate all of its electrons. And what I wrote for you before we had a break was all of the electron energy levels and sublevels, the maximum number of electrons that can fit in each, and the order that they fill. So this is the lowest energy, all the way to the highest energy. Do we have questions? Questions about how we drew the orbital diagram? Don't so much focus on what the order is here. Just know that this is the order. Okay, what's your question? Yes. And what I did underneath is just a way to check your work. Other questions? And no problem. Are there any other questions? It may just be, okay, I just need to practice this. But if we were to walk through another example, do you think that you'd be able to do it? You'd at least be able to draw the arrows if I gave you the lines. Yes. Yes. Okay. So that's the place I'm trying to get you to be, where, okay, if I could walk through another example, I think I'd be good. That's what we're trying to do here. So you will need to, I want you to focus on doing your mastering chemistry homework. I'm not giving you an additional chapter check-in because the chapter 4 is big. But hopefully doing that homework will give you the practice that you need. But if you run into issues, office hours, or send me a message through course messages. So we've got the full order of how to fill the electron energy levels. And that's where we're at. So we're going to break down the periodic table based on the different blocks that show which sublevel is being filled. And I'm going to write in all the different energy levels on the periodic table. I would highly recommend that if you don't have a periodic table printed out right now that you can write on, when you get a chance, make the sheet that I'm about to make. Or you can print it out from the PDF. So this is the periodic table that you're going to get with all of your exams. It's got the group numbers. You've got the names and the symbols for all the elements. It's got the atomic numbers, all that good stuff. What we're going to add to it is about the energy levels and sublevels. So as I said, each row in the periodic table, that's the same thing as an energy level. Notice that I'm not labeling the two rows that are below the periodic table because these are really in here, okay? So we've got our 7 energy levels. And we said that we've got S, P, D, and F in terms of sublevels. The way that the periodic table is organized, the elements that are filling the S, P, D, and F orbitals are all grouped together. I'm going to do different colors for each of the different blocks. The first block is the S block. So all of these elements are filling the S orbital. We've got the 1s, and this also includes helium, which I know is all the way on the other side of the periodic table, but that's just because helium is also a noble gas. But helium is a part of the S block. We're filling the 1s, 2s, 3s, 4s, and so on. So if I ask you what orbital is magnesium filling, you should tell me it's the S orbital. We're going to skip over the middle of the periodic table and go to the far right. This is the P block. We're filling the P orbitals here. So remember how we did neon and fluorine? The last orbitals that we were filling were in the 2p. They're also in the P block. Same thing for silicon. We were filling the 3p. So that's the P block. The next thing that fills is all of these transition elements. This is the D block. You're filling the d orbitals here. And the final block is the F block, which is below the periodic table. And it's filling the F orbitals. Let me go back and fill in all the D's. So this is the periodic table. When you're writing electron configurations or you're drawing orbital diagrams, knowing this information about how the periodic table is set up or organized will be very, very helpful to you. So make sure that if you don't have this now, if you weren't able to do it along with me, that you go back, print out a copy, and do this, and have it in your notes. Use it with your homework. It will help you. It will help you a lot. For your exam, you can't use the one that you've pre-made, but you can certainly recreate it. So print it out, recreate it without your notes, and use that to take your exam. There's no harm in jotting down the things that you know and using that on the exam. So if nothing else, make sure you have this in your notes. Is that clear? Okay. So I said that we can write electron configurations to show where the electrons are in an atom. Let's walk through that. So I'm going to walk you through how to do that for phosphorus. I'm just going to quickly jot down the different levels that we're going to need. I'm not going to fill out the whole table. So we're really just going to need this part here, because phosphorus is in the third period. So there's the full electron configuration, which we're going to write first. And then there's the abbreviated electron configuration. For the full one, you're going to start with the 1s. You always start with the 1s. And we're going to fill it because we have not reached phosphorus. So there's 1s1, 1s2. Then you go down to the second row. We're back in the S block again. And we're going to fill it because we have not reached phosphorus. Then you're going to walk across the periodic table to the P block. And you're going to put electrons in the 2p. You can hold a maximum of 6 electrons there. So we're going to fill it with 6 because we're clearly not at phosphorus yet. Now we're in the third period. We're getting closer. We're going to fill our, oops, I realized I wrote 3p there. So that's the 3s. We're going to fill our 3s. Then we're going to go across to the 3p. This is where we're going to slow down because we are in the neighborhood of phosphorus. And you're simply going to count how many electrons you have just by checking off how many elements are between you and phosphorus. So 1, 2, 3. Notice that I put a 3 there. I did not put a 6. I put a 3. Phosphorus has 15 electrons. So if we total up all of these superscripts, all these little numbers, it should equal 15. Well, we know 2 plus 2 plus 6, that's 10. 2 plus 3 is 5. So we have 15 electrons. So we're good. Were you able to follow how I literally walked across the periodic table until I got to phosphorus? Did that make sense? Sure. So just to recap, we start with the lowest energy level. So that's energy level 1. We're starting with the S sublevel. That's all there is in energy level 1. And then we fill that. We've got 15 electrons to place for phosphorus. The 1s can only hold 2 electrons. So we write 1s2. That's the first part of our configuration. Then we move to the second row, which is the second period. We're still in the S block. We can only fit another 2 electrons there, and we've got a total of 15 to place. So we can add another 2 and be safe. So we fill up the 2s with 2 electrons. No. So the 2, that's the energy level. So that's the row number. So we're not saying that we have 2 s orbitals. We're saying it's the s orbital in energy level 2. Okay. Then likewise for the 2p, there are 3 p orbitals in the energy level 2. And since each orbital can hold 2 electrons, we can hold a total of 6 electrons in the p sublevel. So we fill the 2p with 6 electrons. At this point, we've only placed 10 electrons. We still need to place another 5. So we move on to the third row, or the third period, which is where phosphorus lives. So we're in the town of phosphorus, but we're not in his neighborhood yet. We're back in the S block, so we're at 3s. And the s orbital can only hold 2 electrons. So we fill it with 2 electrons. And now we're at 12 electrons. We need to place another 3. So we move to the 3p. And again, this is the order that I gave you, that long string. We're just going in that same order until we've placed 15 electrons. So we're in the p block, which can hold a maximum of 6 electrons. But we've placed 12 already. We only have 3 more to place. So we put those 3 into the 3p for a total of 15 electrons. Yes. So we're filling up the energy levels in the order from lowest energy to highest energy. So you go across the periodic table, all the way across, before you drop down to a new row. Are there any other questions? Because that was just the full, and let me label that. That's the full configuration. We still have to do the abbreviated configuration. The abbreviated one is a bit easier. We know that phosphorus is in the third period. The abbreviated configuration uses the noble gases to take up all of the complete rows. So neon, we did the electron configuration for neon sort of kind of when we did the orbital diagram. And it had the 1s full, the 2s was full, and the 2p was full. Well, that's kind of what we have here. That is the configuration for neon. So instead of writing all that out, you can write neon in brackets. So you're always going to look for the noble gas that is in the period above the element that you're looking for. We're looking at something in the third period. So we have to use the noble gas from the second period. Then you have to write out the part of the configuration that gets you from that noble gas to the element on the periodic table that you're interested in. In this case, we have to fill in everything on the third row. That's your 3s2 and 3p3. You may be hearing my daughter in the background from time to time. I apologize. She is a loud and lively toddler. And my husband is, taking care of her. So hopefully those sounds are endearing and not off-putting. So this is the abbreviated form. We've used a noble gas to signify the 1s2, 2s2, and 2p6, because that is what its configuration is. And then we filled in everything between neon and phosphorus. Are there questions on that? We're going to do more examples. So if it's can we do more practice, the answer is yes. But tell me how you feel about that. Is it like, this doesn't make sense to me at all? Or, okay, I think I'm ready to walk through another example. Yeah, we're going to do more practice. So let's move on to another example. This time we're going to write configurations for iron. So where is iron? What period is iron in? Iron is in the fourth period. How many electrons do we have to place for iron? We've got 26 electrons. That's right. I'm going to write in each of these levels. So that you can help me as we go along. We've got 26 electrons to place. We always start at the beginning. It's a pretty good place. In n equals 1, in that main energy level, all we have is the s sublevel. And there's one orbital in there. So for the 1s, how many electrons can I put here? I can only fit 2. Each orbital fits 2 electrons. Now I'm ready to move on to the second row, because all there is in n equals 1 is 1s. In the second period, we've got the 2s and the 2p. The 2s is lower in energy, so we're going to fill that first. And just like the s sublevel in n equals 1, it can only hold 2 electrons. Then we scoot across to the p block. How many electrons am I going to place in the 2p? Exactly. I'm going to place 6 electrons because there are 3 p orbitals that can hold 2 electrons each. And if you look at the p block, in each portion there's 1, 2, 3, 4, 5, 6 elements. That means that there's space for 6 electrons. Now, so far, we've only placed 10 electrons. We have 26. That means we've got another 16 to go. Let's move down to the third period. What am I filling next? I'm going to fill the S. Since we just came back around to this third row, we're in the S block. We always fill the S first. And it can only hold 2 electrons. What do I fill next? Exactly. I'm going to fill the 3p next. And it can hold 6 electrons. Where do I go from here? I have to go to the 4s because we filled everything so far in order up until the 4s. So right now, we add another 2 electrons. So we've got 20 electrons placed if we have everything filled from the 1s all the way up to the 4s in proper order. What is the next level that we fill? And level and sublevel. We're in the 3D. And we've got 1, 2, 3, 4, 5, 6. So that is the full configuration for iron. How did that feel? Does it feel good? Do you feel better than before? Or is it still about the same or very shaky? So this just takes some practice. Now let's write the abbreviated form. We said that iron is in the 4th period. And for the abbreviated notation, we need to look at the noble gas that is in the period prior to the one that our element is in. So if we're in the 4th period, tell me which noble gas we're going to use to represent the bulk of our electron configuration. We're going to go up to the 3rd period, and that is argon. Does that make sense to everyone? So we've got everything covered up to here. So that AR in brackets is everything from the 1s up through the 3p. Now we just need to fill in everything between argon and iron. Everything in that 4th row. And that's the abbreviated version. Yes. So it may not necessarily be 2, but yes. The pattern is always to use the noble gas in the period above the one that contains your element. And then you fill in the rest between that noble gas. So argon is here and iron is here. You have to fill in everything in between. So if we were doing zinc, it would still be argon for the core and 4s2, but instead it would be 3d10. Does that follow? Okay. Other questions? Yes, what's your question? So in that case, so you typically wouldn't write the abbreviated form for a noble gas. But yeah, you would have to use neon and then fill everything else in. You can't say that the configuration for argon is argon. That's, you can't say that. So yes, you would. You're welcome. Other questions? If you're ready to move on, you can give me the thumbs up. This is going to take practice. So if you don't feel like you can go off and do a problem on your own yet, that's okay. practice, watch the video, do some homework, hit me up in office hours. All right, so let's move on. The last piece is trends in the periodic table. So we talked about where the electrons are. We've talked about what those energy levels are and what they mean in terms of bigger N equals bigger energy and things like that. The placement of the electrons, that tells you a lot about the type of chemistry that you can do. It also tells you about the size of your atom. It can tell you about ionization energy and metallic character. So we're going to go over those three trends, and I'm going to kind of flip back and forth between the summary table, which has what the trends are, and a periodic table where I'm going to draw in the trends. I again recommend that you have a periodic table that you draw on to put these trends on your periodic table. So the first one that we're going to cover, it's not 100% a trend per se, but it is information that you can glean from the periodic table. We're going to talk about valence electrons. Valence electrons are in the outermost energy level. So from what we were doing before, we had 4s2. That is the outermost energy level. So those would be valence electrons. Those are the ones that are involved in chemistry. For the representative elements, which we're talking about groups 1A through 8A. So like if we go back to a periodic table, all of those that I just circled are representative elements. So that's what we're talking about here for this trend. For the representative elements only, the group number tells you the number of valence electrons. So if you have something that is in group 3A, it has to have the A behind it. Then that tells you that you have 3 valence electrons. So those electrons are available to do chemistry. Is that clear what valence electrons are and what the trend is for the representative elements? Okay. So just real quick. Oh yeah, question. Sure. Let's try to do these like a learning check question, just A, and then check back in and let me know if it makes more sense to you. Is that fair? Okay. So use the periodic table to write the group number, the period, and the valence electron configuration. So I will go through the first one because this valence electron configuration sounds like it's scarier than it really is. So on the periodic table, you're going to find calcium. What is the group number for calcium? So you're going to want to use the one with the A behind it. So put 2A, okay? But it is group 2. There are 2 different ways that the groups are labeled. The ones with the A and B give you a little bit more information about which elements are representative elements and which ones are transition elements. So calcium is in group 2A. What period is calcium in? It's in period 4. So you just count how many, what row it's in, right? Now, going back to when I was drawing all that stuff on the periodic table with the different blocks, which block is calcium in? S block, P block, D block, or F block? It's in the S block. So that means that it's going to be filling its S orbitals, and it means that the 4s electrons are the valence electrons. So if we were talking about potassium or sodium, those are also in the S block, and their valence electrons would be in the S sublevel. So we've got part of the electron configuration just from knowing the period and which block. Now you just have to count. Calcium is in the second group. There are 2 valence electrons. So this is your configuration. Does that last part make sense about the valence electron configuration? I know you got the first 2 parts down. Question, go for it. Correct, because we just care about where the valence electrons are, and those are in the outermost energy level. Yes, go for it. Mm-hmm. So let's try this second one. Now we're looking for lead, which, if you don't know your symbols yet, that's Pb. So tell me what the group number is. We are in group 4A. So you find lead. It's underneath tin, which also has kind of a funky abbreviation, which is SN. But it is a group 4 element. Or 4A, excuse me. What period are we looking at? So what does our configuration look like? You don't have to worry about making sure that the number is a subscript for the number of electrons. But just tell me, we need the energy level, the sublevel, so SPD or F, and then how many electrons are in it. Think about what block it's in. So it's definitely the 6p. But we have more than just 2 valence electrons. everything that is in the energy level 6 is going to be counted as a valence electron. And when you look at the group number for lead, it's 4A. So that tells you there should be 4 electrons, right? So we have to break it up. We've got 6s2 and 6p2. So that one was a little bit trickier because it's like, oh, well, it's in the p block, but where do my other electrons come from? So every electron in the outermost, which you can read as the highest energy level, is a valence electron. So that one was a little bit trickier because we had to include the s orbital and the p. But we should know already that there are 4 valence electrons just by the group number. This is something that you're going to have to practice. And once you have the electron configurations down, then writing the valence electron configuration will be even easier. Yes, question. Okay. So what I'll do is I'll quickly write out what the abbreviated electron configuration is for lead. It is in row 6. So I'm going to look at the noble gas in row 5, which is xenon. Then I'm going to walk across the periodic table. We fill in the 6s. We fill in the 5d. And then the p. We're looking at the outermost energy level. So that's the one with the highest number. Everything that has a 6 is what we care about. So these are the electrons that are the valence electrons. They're in different sublevels, but they're still in the same main energy level. Does that help clarify a little bit more?
Yes, thank you.
You're welcome. Is there another question? So you'll definitely want to do some more practice. Look at your homework early. Hopefully you took the advice of do the stuff from what we covered last week as best you could, so that you just have the work from 4-6 through 4-8 to do this week, because the electron configurations might take you a little bit. In the interest of time, we're going to move on to the next trends. And then if there's a little time after, we can circle back around to valence electron configurations. But we'll likely just have to cover it in office hours if you need some extra help. So Wednesdays 2 to 4, that's the time that is set in stone for every week. If that does not work for your schedule, then you need to send me a message through course messages and set something up. So Lewis symbols represent the valence electrons as dots. So you write the symbol. Let's say we're talking about iron. Oh, I'm sorry, we were doing lead last, not iron. So if we were doing lead, we said that it had 4 valence electrons because it's in group 4A. You're going to write the symbol for lead and write a dot for each valence electron that you have. Notice how I didn't double any of them up. You want to go around and fill each side with 1 electron first, and then double up. For example, if I had fluorine, fluorine is in group 7A. So it has 7 valence electrons. You fill in the first 4, then you go back around and fill in the final 3 for a total of 7. So does that make sense on how to write a Lewis symbol? It's also called an electron dot symbol. And I promise the stuff that we're covering now is much easier than the configurations. So you can breathe a little bit easier. So let's try. I'm going to do this one for you because you can't really show it in the chat. But just try to jot it down in your notes real quick. The electron dot symbol for N, that is nitrogen. I will tell you, it is in group 5A. So I'll give you a head start before I fill it in. Group 5A means 5 valence electrons. So that's what you need. You need 1 pair, and then 3 of them are alone. Likewise, you could have something that looked like that, and it would still be acceptable, as long as there's only 1 pair, and then 3 lone electrons. So are we good on that one? Great. So here are the remaining trends for the periodic table. We've got atomic size, ionization energy, and metallic character. The first one we're going to cover is atomic size. As you go from the top of a group to a bottom of a group, you're going to increase. And I'm going to draw this on the periodic table as well. As you go from left to right across a period, you're going to decrease. So remember, each row means that you're increasing the energy level. And as you get bigger energy levels, your electrons are further and further away from the nucleus. So that's why your atomic size increases as you go down a group. As you go across a period, you're adding protons and electrons, but you're not making your energy level any bigger. So if you're filling in the 2p, you're still in the same level 2 energy. So you're adding protons and electrons, and you're actually bringing those electrons a little bit closer to the nucleus. And that's why the size decreases. So on your periodic table, and I would recommend using different colors, atomic size decreases, or excuse me, increases. And as you go from left to right, atomic size decreases. So that's the first trend. And I'm going to flip-flop between these last two slides so that I can continue to draw and show you kind of what you should have at the end of this. So we covered atomic size. Now we're going to talk about ionization energy. Ionization energy is just the amount of energy that it would take to pluck off one of those valence electrons. As you go from the top of a group down to the bottom, those electrons are getting further and further away from the nucleus. So your ionization energy decreases. As you go from left to right, you're again increasing the number of protons, but you're not making your energy level any bigger. So those electrons that you're adding on, they're being held a little bit more tightly. So that ionization energy is going to increase across a period. Now I'm going through this a little bit quickly, but I explain it much more slowly in the YouTube video. So make sure that you do watch that and take notes if this is a little too fast. We're coming up towards the end of class, and I just want to make sure that we get through this last part. So on your periodic table, you're going to want to choose a different color. And you're going to want to write about ionization energy. And we said that it decreases from the top of the group to the bottom. And as you go from left to right across a period, it increases. So it's the opposite of atomic size. The final one that we're going to cover is metallic character. And that just talks about how easy it is to remove a valence electron. Similar to ionization energy, but not quite. When we say metallic character, the more metallic character something has, the easier it is for an electron to be drawn away. It's going to follow the same trend as atomic size. So as you go from the top of a group to the bottom, metallic character increases. As you move from left to right across the periodic table, metallic character decreases. And that makes sense because on the far right of the periodic table, what do you have? Nonmetals. So it makes sense that everything on the far right side would be low in metallic character. So I like to group metallic character and atomic size because they're the same trend. So those are the trends that you're going to need to know for the periodic table. And you'll need to give so hydrogen. We're looking at hydrogen. Which of these atoms is bigger than hydrogen? And, well, that's pretty much everything, right? Magnesium. Which one of these elements has less metallic character or more metallic character? So you would say less metallic character, then you would go with beryllium, let's say. More metallic character, you would go with calcium. So you need to understand how these trends work so you can compare different elements in different areas of the periodic table. So is the expectation clear about how you need to understand and interpret these periodic trends? Yes. Yeah, it's just an and sign. So we're not going to do this learning check, but I want you to make your periodic table and then use this to test yourself so that you can, given these three elements, label which one is the largest, which one would have the highest ionization energy, and which one belongs to group 5A. And if you have questions about this learning check, you can shoot me a message through course messages, or you can drop by office hours. The final slide is always going to be reminders, as long as I remember. So you have your Chapter 4 Mastering Chemistry homework and quiz due this coming Sunday, which is the 27th. Get it done. It's a kind of a big chapter. You want to make sure that you get as much of it done as possible. And that's why I'm not giving you another chapter check-in this week, because I want to make sure that all your effort is going towards the Mastering Chemistry, which is the bigger portion of your grade. Remember that the chapter check-ins, those are participation. That's 10% of your grade. Important, I can give you specific feedback, but it's not the largest part of your grade. So please, please, please get that Mastering Chemistry work done. Exam 2 is coming up the week of October 5th. It's going to cover chapters 4 through 6. So we're going to be finishing up chapter 6 the week of the exam. Unfortunately, that's just how it worked out. So you're definitely going to want to make sure that you stay on top of watching the videos, because we're going to be doing chapter 6 and exam review, and then you have an exam. Office hours will always be available, but you definitely need to stay on top of your homework and assignments so that you know which parts of the chapter you understand and which parts you need more help on. And then finally, again, the millionth plug for office hours. So they're set in stone, 2 to 4 p.m. on Wednesdays. So we're not changing how you join office hours. We're just setting the time based on what everyone across all of my classes chose. If this time doesn't work for you, you can send me a message and set up an individual time. I would prefer it to be Monday or Wednesday. However, if that does not work for you, then we may still be able to work something out. So don't shy away from talking to me or coming to me just because you can't do Wednesdays from 2 to 4. I know a lot of people requested other times. It's just that this one time got the most people. So please come to me. If you have any questions about anything that we just covered, this is the time to ask. Otherwise, if you're good to go, you're free to go.